Please. Yes, so great, János. So we will start. So good morning, everybody, and welcome to the seminar talk. It's a great pleasure to have today János Pach, and János is usually a great speaker. You can trust my word, but you will see it yourself in a few minutes, and he will talk about grasshoppers problem and how you can solve it using linear algebra. Right. Please, János.
Okay, thank you very much for the introduction, Benny. I am not sure if it was appropriate because, you know, if you tell that someone is a good speaker and then gives a lousy speech, then I hope that everybody will blame you for that and not me.
Exactly. I'll take all the blame for János.
Very good. Thank you very much. Also, yeah, I have a great afternoon. It's maybe still morning in Europe, but in China it is the afternoon, and I appreciate that at this afternoon hour you still try to concentrate on mathematics. And so let me start. I was planning to talk about two applications of linear algebra. There are many applications, and as you probably learned in the course or in subsequent courses, somehow linear algebra turned out to be a very useful tool in many combinatorial problems. But this is the problem I'd like to talk about is kind of a mixture of geometry and combinatorics. You will see. It starts with a problem that was asked in the Moscow Team Olympiad more than 20 years ago. A beautiful question. Actually, it's an interesting Olympiad. As I found out, it was an oral Olympiad. So this was the oral part of the Olympiad. So actually students had something like 10 minutes to think about an answer. And I think that it shows that they had pretty good students that this question can be asked, because most adult mathematicians who are asked this question, well, either see the answer immediately or can think about it for hours. Anyway, so this is the question. So here is, I drew some grasshoppers, not as beautifully as in this amazing picture where there are millions of grasshoppers, but that's my best attempt. And what happens is that you assume that there is a fixed number of grasshoppers sitting in the plane. I assume that the grasshoppers are pointwise, meaning that not as big as in this picture, but they are sitting really at a point. And you can take any of the grasshoppers and it can jump over any other grasshopper and land on the other side at the same distance. So imagine that the grasshoppers are in the plane. So what you can do is that you take one grasshopper and kind of take its mirror image across another grasshopper. And that will be its new position. Then again, you can take any other grasshopper and that can jump over any grasshopper again. And they are kind of hopping around in this way. And the question was the following. Assume that originally you have only 4 grasshoppers and they are sitting at the vertices of a square. And then they will jump around in the way I just described. So the number of grasshoppers doesn't change, so that I will always have 4 grasshoppers. But the question is that can I attain that after a finite number of steps, the grasshoppers will be sitting at the vertices of a larger square? And the answer to this question is that no, it cannot happen. And let me show you a figure for a second. Not a very complicated one that shows that why this is the case. So originally, these little circles, if you see what I am pointing at, these 4 little circles are the original positions of the grasshoppers. And then I take one grasshopper, it can jump over another one. But what you need to notice is that the 4 vertices of the square, they actually determine a square grid. You imagine that the distances between the neighboring grasshoppers is 1, then it is a unit integer grid. And if you start with a unit integer grid and the grasshoppers are jumping around, then at every stage, all the grasshoppers will be sitting at grid points. You cannot get away from the grid point. So if you start from a unit square and you jump around, then you can always have then the grasshoppers will always be on grid points. So this was the picture. So if they are always on grid points, the smallest square is the unit square on this picture. So maybe they can end up in a position where they are sitting you know, at the vertices of a larger square, but definitely they cannot end up at a position where the grasshoppers are sitting at vertices of a smaller square. However, notice that this whole game is sort of reversible. So if you have a position of the grasshoppers and you start do a jump, then this jump can be reversed. So if you could end up in the vertices of a larger square, then look at those larger square and reversing the steps from the point of view of that larger square, you could end up in the vertices of a smaller square. But we have seen that it's impossible to get into the vertices of a smaller square, because in the grid, the smaller square is the unit square. So this means that this is the solution. You cannot even get into a larger square, because then reversing the steps from that square, you could get into the vertices of a smaller square, which is impossible. Okay. Now let me go back to the talk. So and make it full screen. So here we are, and then you see the name Florestan Brunck, whose name appeared in the cover page. So he heard this problem and immediately asked that, okay, so can we do the same if originally the grasshoppers are sitting at the vertices of a regular pentagon? Can we jump around, and can they jump around and arrive at a position where the grasshoppers sit at the vertices of a larger regular pentagon? Well, he popularized this problem and talked to several people about it. And so what I'd like to do here is to tell you some arguments that we came up together with Gábor Tardos. which kind of led to a result that definitely surprised us and also surprised Florestan. So for this slide, I denoted by C of n a regular capital N-gon, and for reasons that will be for some reason technically good, this capital N is small n plus 1. Now, so the theorem that we proved was the following: that if the number of vertices of the regular N-gon is not 3, 4, or 6, then after a finite number of moves, the capital N grasshoppers actually can move into new positions where they sit at the vertices of a strictly larger regular capital N-gon. So the triangle is obvious. That's a trivial case. The square we have just seen, and actually the hexagon you can also prove in the same way. You just the grasshoppers are kind of jumping around not on a square grid but on a triangular grid. That's all. But for all other values of n, the answer is that yes, they can do that. Now, this is a very specific question, so we kind of generalize the question. So in general, we have a configuration of points in the d-dimensional space, and this we denote by capital P. So it is in the d-dimensional space. I will always draw planar figures, because that was our original sort of problem of interest. And so here are the points P1, P2, P3, Pn. And there is a point P0, so that's why I denoted the number of points by n plus 1, because there is a special point, and there is a special grasshopper, if you wish, which is, I call a stationary piece or stationary grasshopper, because this is not allowed to jump. So other grasshoppers can jump over it, but this is not allowed. This always remains in the origin. And you will see that it makes technically our life a little bit easier, but it's not an important restriction. So then, if we agree...
János, sorry, so in the original question, what is P0?
P0 is just one of the grasshoppers. I call that point of the plane any point of the capital N-gon.
I understand, but in the original question, all grasshoppers can jump, right?
All of them jump, but you will see in a second that it makes no difference from the point of view of the answer. It is no difference if I restrict one of the grasshoppers and not allow it. You will see in a second. So, but the good thing is that now that I fixed one of the points in the origin, the remaining points, little m points, I can sort of represent them in a matrix, right? Matrix which has little n columns, and since I am in D space, each of the columns is of length little d. So this is a D by n matrix which describes the configuration of the piece grasshoppers, so let's call them pieces, like in a game. Okay. And now we do the following, and this is how linear algebra comes into the question, comes into the picture. that I define elementary involutions. So what is an elementary involution? The word involution usually in mathematics, it just means that if you repeat it, then you get back to the origin. It's a transformation. If you repeat it once more, then you get back to the original. It's like, if you take the mirror image of something about a point or a plane or whatever, then if you do it twice, then you get back to the original position. So there is one kind of jump when I took a piece, pi, and I jumped over the stationary piece. So then this pi will end up in the position pi prime, which is just negative pi, right? Because this was the zero. So this, so if you think about the matrices that describe the configuration, this corresponds to a very simple matrix transformation. So I looked at the original D by N matrix, and then I multiply it with this matrix AI0, which is almost the same as the identity matrix, except that in the ith position of the diagonal, I have a negative one. So if I multiply the matrix of the original positions of the pieces by this matrix, then one of the columns, so to speak, will switch into its negative, and this corresponds to replacing piece number I by its negative, by this jump. And similarly, if I can tell very exactly that if a piece pi jumps over another piece pj, then it will get into this position, which is negative pi plus 2pj. And this will correspond to a multiplication of the matrix by aij, where aij is again almost like the identity matrix. In the ith position, I have a -1. In the ith and in the ith column at the jth position, I have a 2 because of this. So these are these two elementary involutions, and obviously, if I look at an n by n matrix A, which is generated by elementary involutions, then if I multiply P by such a matrix A, then I can get into that position just by using a series of moves of this kind. So the question is that how can I tell if a matrix can be generated by these elementary involutions? And it turns out that it is fairly easy to tell that. There are only two conditions have to be satisfied. So the first condition is that the determinant of that matrix has to have absolute value 1. Well, clearly, if a matrix is generated by elementary involutions, then it will be true, because each of these matrices has a determinant +1 or -1. So if I take the product of these matrices, then the determinant will always remain +1 or -1. And the second condition is that if I look at the matrix A, then the diagonal elements of the matrix should be all odd, and the off-diagonal elements should be even. Again, this is true for these elementary involutions, and this property gets preserved. An elegant way of saying that is that if I have a matrix A, which is generated by elementary involutions, then A is congruent to the identity matrix modulo 2. It means precisely that in the diagonal all the elements are odd, and in the off diagonal all the elements are even. So now I have showed in only one direction that if it is generated, then these properties are true. But the other direction is very easy too. So let me just quickly go through that, but it's not. You will get the slide so you can check it for yourself. So if I have a so for the other direction, I have to show that if I have a matrix that satisfies these two properties, the determinant property and parity property, then really it can be transformed into the identity matrix by multiplying columns with -1 and adding or subtracting from a column 2 times another. And then this is the way how you prove it. You just prove it by induction. So you look at here is the whole proof. You look at the last row. So in the last row, if you find two entries, so that one entry has bigger absolute value than the other entry, for instance, they are positive. One entry is larger than another entry, and both of them are positive. Then you simply reduce this largest entry by subtracting twice the smaller entry from it. Then it may jump to the other side, but anyway, you got rid of this large value and reduce. In this way, you can reduce the value so that at the end, you don't have different values. You can have two different absolute values, 0 and plus minus a or some a. So actually, if this means that in the last row at the end of this reduction, you have zeros, a's, and negative a's. But if you expand across the last row this determinant, then if a is not equal to 1, then you couldn't have that the whole matrix has determinant 1. And that was one of my conditions. So a must be 1. So this situation really must look like that. Moreover, that 1 must be on the last entry, because in the whole process, the parities didn't change. So if I have only zeros and ones and the parity didn't change, then in the diagonal, this thing should be 1 and all others should be 0. And then I reduce the problem to a smaller problem, and I am done by induction. So it's really trivial. Okay. So now I'd like to characterize, so in general, in this general sort of setting, that if I have an initial configuration given by a D times N matrix whose columns correspond non-stationary pieces, then using these elementary evolutions and their combinations, what are the positions that are reachable? So if I keep what we have seen, if I keep the stationary piece at 0, then it's precisely those positions are reachable, which whose matrix is P times A, where A is generated by elementary evolutions. So now I come to the answer to Benny's question, that what happens as in the original problem, when there was no stationary grasshopper, the zero grasshopper can also jump. And it turns out, and it's very easy to prove that if I allow the stationary grasshopper or piece to jump too, then I can only get into translates of what I can get in the other way. In fact, I can tell you exactly that translates by what, because I look at all reachable positions that zero is stationary, and I can translate them by the vectors that I can get by multiplying p, or rather 2 times p, by an integer vector, or multiplying p by an integer vector whose every coordinate is an even integer. And so let me just show you this figure to sort of illustrate this, so you can easily convince yourself. So what I like to illustrate only that you can get into positions that are the originally reachable position where zero is stationary, translated by such a vector. So to see this, I take any point of my point configuration, and let's look at this first moment where the zero jumps. The zero will jump over this A. Then the new position of the zero will be at 2A, right? So, but what I do at the same time is that with all other points, I also jump over A. And then after that, for the new positions, I jump over the new position of the zero. Come here. And then, if you look at this picture, originally I had this configuration. And after all these jumps, I end up in a new configuration, which is just a translate of the original configuration. And what happened was that the only thing was that the zero, how much did I translate it? By 2A, because the zero got into 2A. And this I can do with each point of my configuration, and with the same point A, I can repeat it several times. So I can translate it by 2A, 4A, 6A, or negative 2A, and so on, and I can combine them. So I am back to. So this means that it is sufficient to concentrate on the situation when there is a stationary grasshopper. Okay. So now let's just go back to the original question, still a little bit more general, where I start from a configuration P, and in this space, there is one of the pieces are at 0, but this is allowed to jump. Then I can tell you exactly when this configuration can be transformed into a larger similar configuration, if and only if there is an m by n integer matrix A, whose determinant is 1, such that P times A is larger, but similar to P. So this actually, we have almost proved this, because we had a theorem which proves this direction under the parity condition, right? So because we have this parity condition, and in this theorem I only had one condition, the determinant condition. So this is kind of stronger. So all we have to do here is that we show that we can drop the parity condition. So the way how to deal with it is the following: that we notice that if I look at the matrix group, the matrices modulo 2, then they form a finite matrix group. So if they form a finite matrix group, then it follows that there is a power of A. I can multiply A with itself 3 times, so that I will end up with I modulo 2. So definitely this A to the T is generated by elementary involutions, because then the condition, the parity condition, is also satisfied. So P times A to the T is reachable from P, but this is not what I wanted to prove. I wanted to prove a little bit more. I wanted to prove that P times A is also larger than similar. So now let me see. I again have this figure for a second. So what we have seen that if P times A was larger than similar to P, then P times A to the T is also, then P times A to the T is lambda to the T times S to the T times P. So where lambda to the T is also larger than T. So actually this automatically guarantees that oops. Okay, that we found an integer matrix for which P times A is larger than similar to P. This is A to the T. Okay. So now back to the regular polygons, so here, so let's look at the situation where I have a hexagon. Actually, for the hexagon, regular hexagon, I know that I cannot end up with a larger similar configuration. But anyway, we now kind of deal with the general case. But the figure is hexagon. Here is the P set 0, or the other vertices P1, P2, P3, P4, P5. And then I look at this matrix M. Here is this matrix M, which in the first row, everybody is -1. It's a 5 by 5 matrix. And then below that, there is a diagonal, 4 by 4 diagonal matrix. The determinant of this matrix is 1. And it's very easy to check that if I look at this configuration P1, P2, P5, and look at the matrix of it, this is a 2 by 5 matrix because I am in the plane. So P1 is really a column of length 2. So M times P, so if I multiply P by M, then actually I get the same configuration as this hexagon, except that it is rotated by pi over 3. So P times M is really similar P, and the determinant is 1. So because of the previous theorem, right? Previous theorem, I found the matrix so that the determinant is 1, so that P time is similar to P. The problem is that it's not larger. The problem is that P times M is actually congruent. I got it by rotation. Now let's again go back for a second to this one. I wanted to show you that what happens now. I try, instead of PM, I try PM square. So, but PM square is PM times M. Now it is PM times N. We have seen that this is S times PM, and PM is S times P, so it's S square P. So this means that PM square is twice rotated, which is kind of obvious. So let's go back. What can I do? What can I do in this situation? So this I just copied from the end of the last slide. So what I can do is a little bit technically, just computations. There is nothing mysterious. So now what I do is that I take any polynomial, and just like I just showed it for M square, for any polynomial, if I take any polynomial and I, instead of M, I multiply P by this polynomial of f of M, this polynomial of M, then what I will get is a polynomial of that rotation transformation times P. So it will always be this f of s will always be of this form. This means that some constant lambda times an orthogonal matrix. And in fact, there is an explicit construction of a good polynomial, which will look like the sum of the first some certain number of powers of my matrix M, and I can choose unless n is one of those forbidden values, then with computation one can check that it's possible to choose I in such a way that the determinant of this matrix will be 1, and the n plus 1 gon that corresponds to P times this matrix A is really larger than P. That was my only problem.
János, so one question. So you always choose this matrix for bigger polygons as well? So it's minus, 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 and then diagonal at the bottom, and it's always gives you...
and the only thing is that I pick a polynomial of it.
Yeah, no, I understand. And it always gives you a rotation.
It always gives you a rotation. Lambda times a rotation. So it's a rotation and scaled rotation. It's always a scaled rotation. And in fact, I can choose it so that the scaling is larger than 1, and the determinant is 1.
Right. And so and it only doesn't work. It always stays 1 when it's triangle and square. And
yeah. Otherwise, I can choose a good I.
Okay.
And it's divisibility properties, and it's a little bit of work, but you know, the algebra, So I can. The paper is on the archive, and one can check the algebra. It's a half a page of algebra. It's not a complicated thing. Okay. Now, let me sort of jump to the second part of my talk, which is a question that occurred to us during this whole process. And it turned out that using linear algebra, it's a little bit more complicated way one can also handle this question. So this is the question that we were thinking about. Okay, we have our little m+1 grasshoppers. We know that it doesn't matter whether one of those is sitting on the origin. Let's assume that because it simplifies the arguments. And then we choose m+1 other points in this space arbitrarily. So we have the original position and m+1. Now we are not so maximalist as before. We don't necessarily want to get from the first position to the second position. What we would like to do is we'd like to get close to the second position. So if I want to be precise, we choose a little arbitrarily small epsilon, and I'd like to jump around with my pieces so that at the end, P0 gets in an epsilon vicinity of Q0, P1 gets into an epsilon vicinity, epsilon neighborhood of Q1, and so on. Pn gets into an epsilon neighborhood of Qn. Can I do that? Now, there is an obvious sort of necessary condition. So the first necessary condition is that the number of grasshoppers should be larger than D. Because if it is not larger than D, then say it is equal to D, then when I'm jumping around, then I am always jumping on the vertices of a grid generated by these D vectors, P1, P2, PD. So I cannot, just like in the original argument of the Moscow Olympiad, I cannot get out of this grid, so I cannot get close to positions where even the points are not on the grid. So definitely, one condition is that the lattice generated by my points P1, P2, Pn, lattice in the sense that I take all integer linear combinations of P1, P2, Pn, or I can say that I take the additive subgroup of the d-dimensional space generated by these vectors, should be everywhere dense. Because if it is not dense, then there will be points so that I cannot even get close to those points, let alone that with the whole configuration, I'd like to get close to a configuration. So this is an obvious necessary condition. So since I am not sure that when I will have to cut short, I tell you the punchline, and then you may be less interested in it, but then I can still elaborate and whatever. So the punchline is that essentially this is the only condition. So if this condition is satisfied, the second necessary condition that this lattice generated by P1, P2, Pn is everywhere dense, then I can get close to starting from the configuration. I get close to any other configuration. So there is a simple lemma that sort of necessary and sufficient condition which kind of helps us in proving the above theorem, then the simple characterization is a very natural characterization. So the lattice generated by my vectors P1, P2, Pn is everywhere dense in the d-dimensional space if and only if there is no vector in the d-dimensional space, non-zero vector obviously, so that the scalar product of each of my vectors pi with this vector is an integer. So let me show you now. So this is a necessary and sufficient condition. So I only show it in one direction in lack of time, but for this again, let me go back to my beautiful figures. Once I do them, you only have to look at this figure. This one I won't be able to tell you. This is so okay. So assume that I found a vector v, so that P1, all of my vectors P1, P2, P3 have a scalar product with that which is an integer. Now, assume for simplicity that this vector v is a unit vector. Makes no difference. So then the scalar product of P1 with W is just the projection of P1 to W. The scalar product of P2 with W is just the projection of P2 to W, and so on. So if all of these things are integers, then if I take any integer linear combination of P1, P2, Pn, the whole additive group, if you wish, generated by these vectors, they will project onto integer points here. I cannot get out of the integers. So this means that if I take any line here which is perpendicular to that, right, then I cannot get close to it. I cannot be, so all the points that are generated will be on these perpendicular lines on V at the integer points. So this is obviously so if I find such a vector, it's a necessary condition. If I find such a vector, then it cannot be everywhere dense. And it turns out that this is an if and only if condition, and the proof of it is fairly standard, and let me just skip it. It is a good exercise. In fact, I would think that in some form or another, crystallographers knew that, because there was a big part of sort of lattice or grid theory that was developed at the end of the 19th century, beginning of the 20th century, which was done by material scientists who, given the X-ray diffraction pictures, they sort of analyzed them, and they found out a lot of things about lattices. Okay, so now again this is the theorem that I announced, and let me write it out. That if I have little m plus 1 points, 1 in the origin, if the additive subgroup is dense in Rd, then for every little epsilon and every n points, there is a sequence of legal moves that keep P0 fixed, that bring Pi into very close to Qi. And just one remark here, that the remark is that if I allow P0 to move, then so this is no restriction, which just made my life easier, that I assume that P0 was at the origin. If I allow it to move, then I can even, by those translations that I mentioned before, you can even achieve that P0 gets arbitrarily close to any point Q0. So this is I think that I end here. So the sort of the proof of this fact requires a little bit more of linear algebra, but nice elementary linear algebra, but it would take another 15 minutes to describe it. Okay, so I hope I didn't disappoint you completely. So, but all the shame is on Benny anyway. So it has been a pleasure to talk to you, and thank you very much for your attention.
Yes, so thank you, János, for the beautiful talk. Indeed, very interesting. So, any questions about János's talk? So János, so is there any kind of follow-up? I mean, some more questions which remain in this area, or is this basically, you think, completely at
So, yeah, good question. This last theorem, it hasn't been written down yet. So this is a follow-up thing. What was before it appears on arXiv, and there, so there are many questions. In fact, I will send you the link to the arXiv paper, because there is a last section there which is full of questions. So you asked that at one point, that how we come up with that, or something like that how we come up with that polynomial for which the linear algebra conditions will be satisfied, namely the determinant will be 1, and also these parity conditions are satisfied, and so on. And this was a matter of algebraic computation. So the problem is that so if you start with any other configuration, so for the regular angle, there was this nice thing, this nice sort of property that that we started with a matrix which was a rotation matrix, right? And we took its powers and we added them up. But assume that you don't start with a configuration which is the regular angle, but for instance, you start with the configuration which is the regular angle with its center. Well, obviously, if you take the square and its center, or the regular triangle and its center, and the regular hexagon and its center, then the original arguments work perfectly well. But if you look at the regular pentagon and its center, then already the algebra is different. And in fact, it took some time for us to prove that in that situation, the case is the same, that unless n is 3, 4, or 6, even if we add the center, we cannot get into a larger similar configuration. So there are many questions, and especially higher dimensional questions. For instance, instead of the why regular angles? In higher dimensions, you can take the Archimedean bodies, right? You can take that the vertices are sitting in the vertices of not an octahedron, but icosahedron, right? Or something like that. So what the answer will be, I don't know. So I think that one interesting question is to come. So we have these general theorems, which are kind of very nice, give some conditions on the matrices, but nice geometric situations where we can apply them, we have very few. In fact, I think that only with what we computed was only with the regular angles and regular angles with the centers. So yeah, there are. So maybe the problem becomes just difficult, but you don't get anything interesting. But maybe you get something interesting, and which is worth examining. And there are other questions there too.
Yeah, no, sorry. Another question one can ask, you're doing it all in RD, right? But you can do it in some other finite groups, for example, right? And then you can study, probably, I don't know, right? It doesn't make sense to get like a copy which is bigger, because bigger doesn't make sense. But for example, you can ask, if you move your configuration, which space of all configuration you can reach, and things like that.
Yes, absolutely, and in fact, we listed that question there too. So this if instead of course, for these arguments to work, it is very important. The whole linear algebra setup, the involutions are important. So if I say that I take one grasshopper which jumps over another one, and it jumps at a distance which is twice as big as the original, for instance, then I also have to allow a move in which it's reversible. This means that I take the grasshopper and it will jump over the other one, and it will land at a distance half of the original distance.
Right.
Because otherwise everything dies. Now probably there are interesting questions there too. But just to adapt, this machinery even to that case, not obvious. It's not obvious. Yeah.
Great. So yeah, very interesting. So I obviously would be happy to look on this section with the questions.
I send it. Yes, I send it.
And people who like the questions also very much encouraged. So I think, János, you live to my promise in the beginning, giving great talks. So I was definitely very happy. So I hope other people were as well. So it was very clear and very inspiring. So thank you again. Yes.
Thank you very much for listening. And also let me say that I will send a link to the archive to Benny. And feel free, this is for everybody in the audience, feel free to send me email if something is unclear, or if you have any other interesting remarks or questions or whatever. I will be more than happy to answer. And I'm sure that the same applies to Gábor Tardos, my co-author. And so don't be shy, write to us.
Absolutely. Great. Thank you very much. So again, it was a great pleasure seeing you. So we can stop the recording.
Okay. Thank you again.
And then next week, again, I invite everybody to come to next talk. It would be Shoham Letzter, and you can see the announcement on the seminar website. So thank you again.
Bye-bye, and have a nice afternoon to all of you, because now it's already the afternoon in Europe too.
Thank you. Thank you, everybody.
Bye-bye.
Bye-bye. Actually, I don't